Now the third differential operator is curl. So regarding curl, one point we can write, it measures how much any field curl or rotates about any point. So just note down this point, then we will try to understand exactly what it means. It is the measure of how much a vector field curl or rotate about any point. Let us try to understand this. For example, okay, before that, this is indicated as cross product of the vector field. Divergence was just dot product, gradient was the multiplication with the field, and the curl is the cross product. So it is indicated by cross product. Second thing that we can say, if it indicates it is indicated by this way, then it means this is applicable for vector field and output is again a vector quantity. Applicable for vector field and output is vector quantity. Finding the curl means we are trying to find the rotation of the field about any point. Suppose this is one point and any field V is rotating anti-clockwise, then the curl of the field is considered as positive. We are trying to find the rotation of field about any point. If it is rotational in anti-clockwise direction, then it is considered as positive. At the same time, if the field is found rotating in clockwise direction, then the curl of that field will be considered as negative. That is fundamental assumptions we are taking here. Now, the third thing that we can consider here, if any field is not having the curly nature, then at any point, then we can say the curl of field is 0. So it is considered as positive, it is moving anti-clockwise. If it is rotating in clockwise, then the curl of field is considered as negative. If the field is irrotational, then the curl of the field will be equal to the 0. So in this case, the field is said to be irrotational. Now we can define the definition of curl. So suppose there is any vector field V and we want to define the curl of V, then it is the maximum circulation of field V per unit area as the area tends to minimize. So in that case we can say the curl of field V, or we can say simply curl of V, both are can be written, is equal to, we can say, the circulation of field V per unit area as area tends to 0. This is the definition of curl. Now if we want to define the curl, then definition of it can be curl, that is cross product of curl of V. Either we can write simply curl of V. It can be the maximum circulation of the field, and maximum circulation of field in a closed path can be written as field in a circulation of field can be written like that, in a closed path per unit area when area tends to 0. This is the full definition of the curl. So this is mathematically we can write. Now if we want to write it in statement form, then we can say curl of field V is the maximum circulation of field per unit area. And as area tends to 0, or we can say area, okay, just write area tends to 0. This is the full definition of the curl of any vector field V. Now mathematically, in Cartesian, cylindrical and spherical coordinate system, we can write it that can be, in Cartesian coordinate system, the curl of vector field V can be written as, so as in the last case, in the case of divergence, we took the help of the differential length to write the divergence. Here also we will take the help of differential length to write the formula for curl. So the differential length in the case of Cartesian can be written as dx ax cap plus dy ay cap dz az cap. Now the curl of vector V can be written as ax unit vectors, ay, az, this is cross product, so the determinant we have to find like that, del over del x, del over del y, del over del z, and here Vx, here Vy, here Vz. The determinant of this will give us the curl of vector field V. Now just for simplicity, try to find the determinant here. Then that will be, to find the determinant for this minus this. So it will be del over del y Vz minus del over del z Vy. Now this is minus Ay. We know how to find the determinant, just I am revising here. This minus this. Del over del x Vz minus del over del z Vx plus Az. For Az we can say Az del over del x Vy minus del over del y Vx. This is the curl of vector field V in Cartesian coordinate system. Now in cylindrical coordinate system, let us write in cylindrical coordinate system. So first thing that is important to write is differential length, and in cylindrical coordinate system the differential length is d rho in the direction of rho plus rho d phi, because here the coordinates are rho phi z. Okay, so differential length in that case is written like that. Now the curl of vector field V in cylindrical form can be written as, so the coefficient here is 1 1, so just multiply the coefficients, that is 1 multiplied with rho multiplied with 1, it will be rho. So in the outside it will be written as 1 by rho. This is to make everything simpler for solving the problem. 1 by rho. Here the unit vectors a rho, second unit vector is a phi, third unit vector is az. Write as it is, like the del over del rho, del over del phi, del over del z, as we have done in the case of Cartesian coordinate system. Here write V in the direction of rho, we can say V rho. Here V in the direction of phi, V in the direction of z. Now compare this with this one. One should be here and here. The coefficient is rho, so rho we will place here and here. The coefficient is 1, so we will place 1 and 1 here. So if we will find the determinant of this, it will be the curl of the vector field V in the cylindrical coordinate system. Now in a spherical coordinate system, just again start from writing the differential length, and hopefully you can remember this. That was the dr in the direction of radius vector and the r d theta in the direction of a theta cap and r sin theta d phi in the direction of unit vector a phi. This was the differential length. With the help of this, we will try to find the curl of vector field V in the spherical coordinate system. Will be, what are the coefficients here? 1 r r sine theta. So multiply the coefficients, 1 multiplied with r multiplied with r sine theta, it will be 1 by r square sine theta. So this will be like that. Here AR, these are the coordinates AR, A theta in cylindrical form and A phi. If we recall, then we find that the coordinates in spherical form are r, theta and phi. Again just write d over d r del over del theta over del phi. Here we will write the component Vr, V theta and V phi. The components we have written. Now here the coefficient is 1, so no need to write anything here and here. The coefficient is r, so just write r here and r here. The coefficient of this is r sine theta, so write r sine theta here and write r sine theta here. In this way, the determinant of this will give you the curl of the vector field V in that direction. Now this is the curl of any vector field V in different coordinate system. On the basis of the curl, theorem is defined, that is a theorem is given, that is Stokes theorem. It states that the circulation of any field, this is circulation of any field in a closed path is equal to the surface integral of curl of the vector, surface integral of the curl of the vector. In statement form we can write, it states that the circulation of field V, circulation of any field V in a closed path is equal to the surface integral of the curl, surface integral of the curl integral of the curl of that field bounded by closed surface. In this way, the Stokes theorem is defined, that is related to the curl of any vector. Consider an example where the coordinates are x and y and field is changing in these coordinates only. This is the field, it remains constant in the direction of x and it don't have any nature in the changing nature in the direction of y. So we have to find the curl of this. field. Just you can say the field is now if okay, field is A. Now we have to find this. So from here we can say that the field remains constant. It is flowing with constant rate in the direction of x. So A can be any constant x. Okay, and in remaining direction it is 0. A x, a y, a z you can say. Okay, write it, no problem. Okay, now we have to find the curl of A. Because this is our requirement to find the curl. As it is rectangular coordinate system, so according to DL we will say AX, AY, AZ, del over del x, del over del y, del over del z. Here the x component we have to write k, here the y component, here we have to write the z component of the field. Now try to find the determinant. In that case it will be this minus this, minus ay, this minus this. So it will be del z constant k minus 0 plus az 0 minus this del over del y constant k. So next thing, ax0 minus ay, the partial derivative of a constant quantity will give you 0 plus 0, okay, minus plus az 0. So what you will get? 0. The curl of the vector field A of this nature is 0. It means this field is not having any curling nature. The field is irrotational. So sometimes the question like this has been asked, if the field is given, show that the field is irrotational, or if they will put any constant here and remaining things will be known to you, they will say try to find the value of this so that the field becomes irrotational. It means you have to show that the curl of the field is 0. Consider another example. Take the xy coordinate and consider the field changing in the x direction, and you can consider this change linear. It means A can be written as kx. A can be written as like that if you are considering linear variation of field. Okay, on the basis of that you have to find the circulation of the field. In that case, as you have done in the previous case, you have to find the curl of field A. And to find the curl of field A, first of all you have to know the A. If you know the A, then you can find the curl easily. So further A can be written as kxax plus 0 ay plus 0 az, and here you can say the curl of A can be written as the unit vector A a rectangular coordinate ay az. Here del over del x, del over del y, del over del z. Here the coefficient of ax means we have to write here ax, ay, az. We have to write this component here, so that will be kx. Here will be 0, here will be 0. Now find the determinant. If you will find the determinant, then you will get ax multiplied with 0 minus 0 minus ay. This is 12th standard mathematics, so I am not giving emphasis on that. This 0 minus del over del z kx plus az, this minus this. So what you will say, del over del y kx minus 0. Okay. Now what you can observe here, 0 minus 0, because this is varying in the direction of x. So partial derivative with respect to z. So it will be considered as constant. So it will be 0. And here same thing will be with that. So it is 0. Again, this field is irrotational, means it don't have any circulating nature. So the curl of field A is 0 again. Now consider this field. What we can say about this field is moving in the direction of x but changing in the direction of y. So we can say ky ax and 0 ay plus 0 az. Field is not moving in the direction of y, so 0 ay. Field is not moving in the direction of z, so 0 az. Just it is moving in the direction of ax, so it will be ax. But it is changing in the direction of y. As we move in the direction of y, the strength of the field is changing. Anyway, this is the statement for field V. Now we have to find, and we wish to find the curly nature of this field. Then what we can say, curl of field V will be again rectangular coordinate system, ax, ay, az, del over del x, del over del y and del over del z. Here you can say ky 0 and 0. Find the determinant. In that case it will be ax 0 minus 0 minus ay. If you will take ay, then it will be 0 minus 0 plus az, it will be 0 minus ky differentiated with respect to y, it will give you k. So 0 0 plus az with minus k. It means the field is having curly nature in the direction of downwards. If upward is considered as positive z, then downward is considered as negative z. It means what the field is having nature to rotate in the direction towards the negative z. It means field is not irrotational, this is rotational.